Hello, and welcome back to all my subscribers. And if you're not a subscriber, why not? Today we're going to do something a little bit different, but we're still continuing on with the Motorola 68K theme. But this time I want to talk about software. I'm looking at writing an operating system, and this is the sort of first phase that I went into. And I just want to go through the things that I've done so far to um, to get here. So the point of this project is to develop a minimal operating system for a Motorola 68K emulator, in this case, with an emphasis on understanding low-level system development and developing an operating system from scratch, and then addressing technical challenges in cross-compilation, file system integration, kernel development, and all of that stuff. So the choice of an emulator allows me sort of rapid development and debugging for any potential issues. And so what I decided to do is to create a virtual machine. Now, I decided to create a virtual machine using QEM, QEME, right? And so this is the QEME. I can, let me just show you the startup that I've got here. So I'm using the emulator. So this is a 68 X68 emulator. I've got acceleration on. I've got 6 gigs of RAM. I've got a hard drive set up, regular network, and then I'm giving it 4 cores, basically. Now, this machine will also run on my Linux box, so I can run this on a Windows machine or a Linux machine. It doesn't make any difference. And I keep the same setup and environment. So that was the purpose. I could control the VM and isolate the tool chain, and I wouldn't have any conflicts with the host system. I attempted to do this initially on Windows. It didn't work, and so I just decided to create a virtual machine that I could run on both Windows and on Linux, and then I didn't have to worry about it. And then I can do snapshots as well for, stable releases and things. And also Linux provides me all of the essential development tools, emulators, cross compilation utilities. I don't have to worry about any compatibility issues when I'm doing it on the Windows host or the Linux host or whatever. And so what we've got here is a Linux Mint Wilma, Linux Mint 22. That virtual platform is a QEMU based virtual machine. Why did I pick QEM over VirtualBox or whatever? Well, um, basically, it offered hardware level emulation, super fine grained control over system configurations. It's compatible with the Motorola architecture. It allows disk images to be mounted and tested within the emulated environment. It's basically more flexible and better suited for low level testing, for my purposes anyway, than any alternative like VirtualBox. And then I had the build essential compiler toolchain, the bin utils, and the cross compilation utilities. So let me log in. I'm not going to log into this window because it's actually painfully slow. And so what I tend to do is SSH into the VirtualBox from the host, which makes things slightly easier. So in here, you can see I did the toolchain build, and I build bin utils, GCC, and new lib. Now, the reasoning behind this was because I needed a cross compiler, and a lot of the pre-compiled cross compilers don't have some of the things I wanted, or they had too much stuff, or I needed an embedded thing. So creating a cross compiler of my own toolchain within this was extremely helpful because I could get rid of any unnecessary dependencies or outdated libraries or whatever. And the custom compilation ensured I had a minimum configuration with no unnecessary features, etc. When I'm working in a sort of a constrained environment like the simulator. Um, So I downloaded all the sources for GCC, binutils, and newlib, which is in an embedded systems C standard library. I configured binutils, I configured GCC, and then I built them, compiled them, and installed them. Now, why use newlib? Well, the raw system will lack a standard library, so you don't get printf or malloc or any sort of thing like that. And newlib is designed for embedded and bare metal systems, and so it's got a minimal footprint, and it still provides the essential the essential C functions. So anyway, I configured and linked newlib during the GCC compilation, and so that allows me, when I build the kernel, to have basic functions without the full standard library being done. So if we go back up, um, to the source code, and just to this dump to FSC was so that I could see how other people were using the accessing the ext2 file system. Now, I decided to pick an ext2 file system, right? Largely because it's simple. It's simpler than the latest versions, though I think they're on version ext4 now. But it's robust and it's suitable for operating system development. It supports standard Unix file systems, symbolic links, directories, etc. So it'd make it easier to extend the operating system if I want to in future. It's got a relatively simple implementation compared to sort of journaling file systems like ext3 and 4. And then so many people are going to ask, well, why didn't you just use FAT32? Well, FAT32 doesn't have modern features like file permissions and symbolic links. It's more prone to fragmentation and data corruption without building recovery mechanisms in, and I wouldn't be able to do that. Also, ext2 is easier to parse directly in the kernel due to its simpler block allocation scheme when you compare that to fat tables, right? So basically what I did was I just did dd to create the image, and then I used mkfs.ext2 to format the disk image, and then that was it. So that's easily done, especially on a Linux machine. So within this emulator, it was an easy thing to do. And then if I go back a bit, we look at the make file. What I'm doing here, let's make this a bit bigger. Don't know if you can see this or not, but to build the bootloader and the kernel. But when I get the image, once the kernel is built, it's relatively straightforward to mount the image file and then copy the kernel into it and then create an output image file. So this is what the top level make file will do. It basically takes the built bootloader and the built kernel, but it loads the kernel into the file system. So the purpose here is to automate the entire build process, including the kernel linking, compilation, copying the binary over to the disk image, and basically ensure that all the dependencies are tracked when it's built. So I can build everything I need from this top level. And then, as you can see, I can go into bootloader, and if I try this, it isn't going to work, by the way. But I can run the makefile here because it's not yet working. But the idea here is I run the makefile here. This creates the bootloader. And in fact, this is an older version. I need to do an update. So the last time I was working on my Linux machine, so I now need to do a pull from my GitHub to get the latest version of this. But anyway, so that's the bootloader. And then over here, I build the kernel. Um, and again, this is relatively straightforward. It just builds the kernel and moves it into the bin directory. So everything, there's two make files, one or three make files, one for the kernel, one for the bootloader, and one at the top level. It basically um, moves everything into the bin directory. So it moves the bootloader bin, the kernel bin, and the image file, which is the image I showed you earlier with this kernel embedded in it. So for the kernel, um, ugh, sorry, for the kernel, the main thing that I need it to do is at the moment not a lot. So um, currently it does pretty much nothing. It just writes a message um, to the default UART, which in the QEM system will send this to the screen effectively. So this is all this does at the moment. It just sends a message to the screen, a simple sort of hello world type thing. Um, Now, what I want in future is I need to initialize the CPU state, check the memory, get the hardware. It needs to do memory management. It needs to do basic system calls like write and exit. It needs to handle interrupt and exception handling, all kinds of things. So the first thing I need to do is just to get a minimum bootloader that loads the kernel from the disk into memory and then jumps to that entry point. So the bootloader is a very cut down version of the one that I had been using for my actual hardware build. But it does do most of the sort of exception handling. But the idea here is that basically it loads up the stack pointer, goes into supervisor mode, jumps to post, reads the kernel data, and then jumps to that entry point, and then that's pretty much it. At that point, the kernel will take over and do everything. Um, and the kernel is supposed to do initialization of memory systems, I/O, interrupt handlers, uh, memory management, basic console, serial communication, input output. All of that stuff is in the kernel, not the bootloader. So the bootloader should just be a basic thing that loads up the kernel and then boots it. And the kernel can be on the disk and it can be of any size, really. It doesn't make any difference because you're loading it from the disk. So the idea here was to do everything on an emulator. Now this VM is run on QEM too, but this is a x86. To run it, I run it basically on the host, either Windows or Linux, and I basically do the same thing um, by running the command within the host. So I build everything on this guest virtual machine, and then I run it, the thing that it built on the host. Um, I've had a few problems with Windows because it doesn't really support um, QEM, rather, doesn't support sort of file sharing and things directly. And so I'm basically SCPing the bin files onto the host machine and then running it from there. So at the moment, there's a bit of uncertainty around how block devices are accessed. So I need to rewrite the kernel and work through that and do various testing. Now, some of the problems and challenges I've encountered are a lot of missing dependencies on the GCC compilation. So I've had to install libraries like GMP, MPFR, MPC, and then reconfigure the build. The bootloader failed to locate the kernel, and so I had to tried to work out why I was not reading it properly. So I initially was going to disk IO and try, and I had some what I thought were working processes. They didn't work. So I created this new directory, and in this, um, there's a good chance this isn't going to work. Yeah, it does there. So the idea here, this isn't the final working one, but the idea here was to go through the block size, get the block size from the super block, get the location of the group descriptor, find the root inode, find the directory structure, and then work through until I can find boot slash kernel. If I show you this with, have I got it installed? No, I don't. Um, but the dump fs will showed me the actual location of this, and then I retrofitted my code around it to work it out. But basically, the idea here is that I need some way to work out the ext2 super block, and then the group descriptors, and then find the file that I want. So I've been working on this. I got this working sort of late last night, and I just need to update the GitHub repository. But so the next immediate steps from this, I'm okay so far. I need to rewrite the load kernel C program to interface with the block device correctly, now that I know how to actually access the super block and the group descriptor within the um, system. I can probably show you some of the code I've been using to try and work this out. But basically, this is the super block and all of the things that it contains. It tells you the number of free blocks, the inodes, frag, everything. And then there's the group descriptor, and the group descriptor is the thing that is telling you where the files are, where the directories are, etc., etc. And then the inode is the actual unit itself, the file directory inode. And so I've been working through this to try and traverse and find the correct directory. Again, this isn't work. This code works, but it doesn't find the thing correctly. So I've been doing a lot of work to work out where the correct offset is to read the group descriptor and the inodes. So there's a fair amount of kerfuffle to get this to work, but I'm a lot closer than I was before. So I just need to rewrite the load kernel function to interface with a block device, because currently, as you can see here, it's going to from main. It's trying to read a file, right? So here it's trying to put the ext file system image. Can't do that inside the system. It needs to run as a block device. So the long-term goal is basically rewrite that so it interfaces with a block device presented by QEM within the machine, get the kernel loaded dynamically during the boot, and then at that point I can start to modify disk IO and things for in-machine execution. So the longer term, expand system calls to allow user mode, implement dynamic memory in the kernel, add driver support, enable multitasking, minimum shell, basic utilities, etc., etc., etc. So this is the very, very, very start of the thing. To be honest, it's been a long time. It took me probably 4 days to get GCC, bin utils, and newlib compiled correctly as a cross compiler. Then I had some problems with the emulators, and then the massive problem of trying to work out how to access the inodes and things in an ext2. From a code point of view, FAT32 would have been easier, probably, just because there's more examples. But for me, I wanted to go with the inode-driven file system. So that's where I am at the moment. I hope you like these sort of videos. If there's anything else you want to know, please leave me a note in the description and I'll try and cover it in a future video. But that's where I'm at the moment. Thank you all very much for paying attention to me today. And if you like these sort of things, like and subscribe and all that sort of good jazz. And I will see you later. Have a good day.